Now, this LFSR or the CLFSR and this counters, they can be used for generating exhaustive test patterns, because all the patterns are generated by these structures. Now, the problem is that this exhaustive testing is good, because it guarantees all detectable combinational faults that are to be detected, but at the same time test time becomes prohibitively large. Okay. So, if number of inputs is more than 20, then you require a large amount of time to generate those test patterns and apply to the circuit. So, for each of these patterns are to be generated by the pattern generator, applied to the circuit, and the response has to be summed up. And the problem is that we cannot stop in between, like you cannot say that I will apply only say first 100 patterns, because there is no guarantee that the first 100 patterns are very good, they can detect large number of faults. Unlike say deterministic testing, where we know that the first few patterns that are there in the test pattern set, they are very good. So, they detect large number of faults and all that. But in case of this BIST policy, so since we do not have any control over the patterns that are getting generated, so we cannot assume that the first 100 patterns will be sufficient for testing the circuit and all that. So, we need to apply all the patterns. So, that way this test time becomes prohibitively large when it is number of inputs is more than 20. So, what is the way out? Way out is to have some pseudo random pattern generated. So, it is a pseudo random testing has to be used. So, here we do not apply all the patterns. So, we apply only a subset of patterns, knowing fully well that I will not get the same level of confidence as the exhaustive testing, but as we have told in some class earlier, that even if you apply some random pattern, so it is normally seen that about 80% of the faults are may get detected by the random pattern itself, random pattern themselves. So, that is why, so it is possible that we apply some pseudo random testing. So, we have got a pseudo random pattern generator. So, it reduces test length, but sacrifice the fault coverage, and it is difficult to determine the required test length and fault coverage, because how long will you run. So, basically what we can do is we can do a simulation, like this is my random pattern generator. So, I simulate this pattern generator for 100 cycles, that gives 100 patterns, and for this 100 patterns we do a fault simulation to see what are the faults that are detected by this. So, that may be one possibility, but of course, there is another issue, like this response analyzer is also not going to check this individual output separately, but it is only going to give us a signature at the end of the session. So, at the end of the session, what are the for each fault we can see whether this gives a different signature or not. For all those faults where we get a different signature from the fault free circuit, so those faults are detected, others are not. So, that way fault coverage becomes an issue. So, it is very difficult to determine the required test length and the fault coverage. So, this maximum length LFSR, it can be used as pseudo random pattern generator, but the problem is that there are certain faults in the circuit which are random pattern resistant. So, the random pattern resistant faults are those faults where the possibility of hitting a pattern that can detect that fault is very low. So, this happens particularly where there are only a few specific test patterns that can detect a fault, and then since it is since we are trying a random generation, so probability of getting that particular pattern generated is small. So, we can modify it, we can modify this maximum length LFSR properties to have some weighted LFSR. So, in the weighted LFSR we change the weight factor. So, we can say that some portions they will have some of the cells they will generate more ones than others. So, as a result there is some weight factor, and the pattern generated is skewed, and this skewed pattern that are generated may be helpful in targeting some random pattern resistant fault. And cellular automata is another structure. So, that is also used in many cases. The idea is that here the individual cells, they depend on its content depends on its neighbors, unlike LFSR where only the first cell is getting the summed up values from different cells. In case of cellular automata, so every cell consults its neighbors, and accordingly based on some logic function, so it computes the next value of the cell. But anyway, there are also the same issues will remain, in the sense that this randomness of cellular automata, so that will also be another issue. So, what is an weighted LFSR? So, weighted LFSR is like this. See, this is a normal LFSR. So, where we have got these cells 1 0 0 1, and we see that this LFSR. So, this is generating, if you just run it continually, so it will generate all the patterns. Okay. So, it is a maximum length one, so it generates it. Now, you see that we put some extra logic. So, this x4 will be x4 output will be 0 only when both this cell and this cell they are 0. When both are this cell when both of them are 1, then only this cell output will be 0. Otherwise, this NAND gate output will be 1. So, assuming that these 0 and 1 are equiprobable, so these two cells are equiprobable in the random sequence. So, you see that the probability of getting a 1 at this point is much less compared to getting a 0, because you will get a 0 whenever either of them is. So, you will get a 0 when both of them are 1. So, the probability of getting a 0 is much less compared to getting a 1, because you will get a 1 whenever any of this cell content is 0. Okay. So, you will get a 1 at this point. Similarly, if you consider say this x1, so x1 will be x1 output will be 1 when either of these two inputs are going to be 0. So, that the probability of getting a 1 at this point is higher compared to getting a 0. So, in this way we can use some weight factor, and accordingly we can choose inputs from these different cells and put them into these gates to get some weighted pseudo random pattern generator. Another way of handling this testing of this exhaustive, another modification to the exhaustive testing is the pseudo exhaustive testing. So, pseudo exhaustive testing it tries to reduce test time while retaining many advantages of exhaustive testing. So, it guarantees 100% stackered fault coverage. So, basically what we are trying to do is, if this is the circuit that we are trying to test. So, in an exhaustive testing, if it has got these inputs, then it will be trying to generate exhaustive pattern for all the 4 inputs, but it may be sufficient that I generate exhaustive pattern for these 2 and I generate exhaustive pattern for these 2. For the remaining one, I do not. So, there is the patterns that I apply, they are not exhaustive when we consider say these 2 inputs. Okay. So, when we consider this pair, so patterns are not exhaustive. So, if you look into the pattern, so here I am applying, so 0 0 0 1 1 0 and 1 1. So, all the patterns. Similarly, here also I am applying 0 0 0 1 1 0 and 1 1. But you see that if you are considering say this input and this input, so it is not exhaustive. So, it is generating only 2 patterns 0 0 and 1 1. So, this is another, this sort of testing, they are called pseudo exhaustive testing. Now, for a circuit, it may be the case that we do not want all these exhaustive patterns to be applied, only at certain input cones of the circuit. So, we want to have this exhaustiveness. So, that way we can have this pseudo exhaustive testing. So, first one is known as verification testing. So, what we do, we divide the circuit under test into m cones, and we backtrack from each output to determine the inputs that drive the output. Okay. And each cone will receive exhaustive test patterns that are tested concurrently. So, what is happening is that, suppose in this particular case, so we have got a 4-2 cut, where n is the number of inputs and w is the maximum dependency. So, if you look into this circuit, so if you take this say y1 output, you see that it is getting input from x1 and it is getting input from x3. So, for testing this gate exhaustively, I need exhaustive patterns only at x1 and x3. Similarly, so this gate y2, so it gets input from x1 and x2. So, again I need exhaustiveness in x1 and x2 only. So, in this particular circuit, so if I can apply a test pattern set such that it is exhaustive for any for all the two inputs, like if you pick up any two inputs. So, I want to apply a test pattern set such that if you pick up any two inputs, so it will have the exhaustive pattern in that. Like if it say this test pattern set has got say 10 patterns, then if you pick up, say if you look into the lines x1 and x3, then out of those 10 patterns you will find that it has got all those sequences 0 0 0 1 1 0 and 1 1, all those combinations are there. Similarly, if you look into x1 and x4 also, you will find that somewhere or the other this 0 0 0 1 1 0 and 1 1, those patterns are there. So, this is this type of pattern generation. So, they are known as this pseudo exhaustive pattern generation. So, this is exhaustive only at only for a subset of numbers, and they are tested concurrently. So, what is happening is that I have got this test pattern set. Now, in this test pattern set, in this particular circuit, if you pick up any two positions, say you pick up say this position and say this position, so it is exhaustive there. Similarly, if you pick up this position and this position, so there also it is exhaustive there. So, these patterns you can apply simultaneously to all the circuit, all the cones. Like if this is my circuit and it has got say these three are the outputs. Now, if you see the input cones, maybe this is one input cone, this is another input cone, this is another input cone. Okay. These are the three input cones. Now, one possibility is that I test these cones separately, okay, one at a time. So, that is one possibility. Other possibility is that I apply the patterns in such a fashion that it is exhaustive for this cone, it is exhaustive for this cone, it is exhaustive for this cone. So, for all this subset, this for individual cones it is exhaustive, but the testing is done concurrently. So, that is what is said here, that each cone will receive exhaustive test patterns and naturally they can be tested concurrently. So, this is one type of testing that is there for exhaustive testing. Another possibility is that we can use some syndrome driver counter, so to generate the test patterns. So, we check whether some inputs can share the same test signal. Like if n minus p inputs can share test inputs with other p inputs, then the circuit can be tested exhaustively with these p inputs only. Now, you see that in this case, if you look into the circuit, now this x4 is nothing but x1 only. So, whatever is x1, so that itself is x4. Now, x1 and x4, so these two whatever pattern will be generated from this circuit, the x1 and x4 are going to be same. Now, if x1 and x4 are going to be same, then if it is possible that for the circuit that we are going to check, this I have got a line 1 which can be shared. This line with the x1, the line to which x1 feeds and line to which x4 feeds, they can be shared. So, if they can be shared, then 3 stage syndrome counter is sufficient. So, it can generate the patterns, and this x1 and x4 they are duplicates, but that can feed the circuit. Another possibility is that some constant weight counter. So, this is the constant weight counter. So, this uses some m out of n code. So, whatever codes are code pattern will be generated. So, this follows this possibility, this one, that is out of n positions at m positions. So, it will generate the code. Okay. So, this is coming from the coding theory, we will not go into the details of that, but this can be generated by LFSRs. So, out of n positions at m, as you pick up any m positions, so it will generate a pseudo exhaustive pattern there, an exhaustive pattern for those m cells. So, this can also be used for this test pattern generation. Combined LFSR SR. So, here what is done is that first we have got an LFSR, and then after that we have got some shift stages. Okay. So, this is a 3 stage LFSR x1, x2, x3. After that, as a 4th stage, we have added another flip flop. Okay. So, this is so at x4 you will get a shifted version of x3. So, that may be sufficient in many cases. So, this uses a combination of an LFSR and a shift register for pattern generation. So, how many such stages will be added? So, that is a question. And so, if W is much less than N, so W, so you remember that N and W, so N was the total number of cells, total number of inputs, and W was the width for which exhaustiveness is needed, width for exhaustiveness. Now, if you have got this W much less than N, but there are more number of cones. Okay. So, in that case, what happens is that this x1, x2, x3, so that may be feeding 3 different inputs of the cell of the circuit. So, there it is fine, but they are generating independent patterns, so that they can be fed. But for the remaining input, we may be able to feed them through some shifter stages. So, x4, x5, x6, so we can add a number of shifter stages, and from those shifter stage, so we can feed the circuit. Okay. So, the technique requires much more tests than other schemes naturally, and when W is greater than N by 2. So, if it is more than N by 2, then of course, there is more number of shifting stages are to be added, and it will require more number of say. But if the number of stages, number of the value of W is less, in that case, in most of the cases, by adding 1 or 2 extra shift stages, so we can generate the test sequence, we can generate the exhaustive patterns for the cells. So, we can do some analysis about their dependency, and we can find that they are going to be independent. Okay. So, accordingly, we can feed them with the patterns. Sometimes we also use some phase shifter. Okay. So, this is previously after this LFSR stage. So, we added a shift register. So, now we add a phase shifter. So, what is done, this x1, x2, x3, so they are summed up and this x4 input is generated. So, this is combined LFSR and shifter approach, combination of LFSR and a linear phase shifter, which includes a network of XOR gates to generate test pattern. So, it is similar to LFSR SR and more test than when W is more than N by 2. So, the performance of LFSR SR and LFSR PS, they are going to be similar. Only thing is that here, instead of using this extra shift stages, so we are using phase shifter by this XOR gate. Another strategy that can be followed is the segmentation testing. So, what can happen is that the circuit may be very large, and as a result and the output depends on more number of inputs. Like here you see that we thought about this policy when these individual outputs, their cone of dependency was much less than the total number of inputs in the circuit. But if it happens that it is not the case, then there is at least one input whose cone of dependency spans over almost all the inputs. There is one output for whose cone of dependency spans over almost all the inputs. Then for testing this output, we have to apply exhaustive pattern for all these inputs. So, that makes it cumbersome. So, all the methods that we have discussed, so they will not be able to solve this problem. So, test length will become too high. So, it is, so in that case, what is suggested is that we divide the circuit into segments. Okay. So, and how do we divide? Like you see that if in the circuit I may have say 2 outputs, this one and this one. So, what we do, we put some multiplexer, and using this multiplexer, so normally maybe the output the input is coming from a far away input, so that this cone includes that. So, what we do, we have some other input multiplexed onto it. So, in the test mode, so this input is changed to this input. So, as a result, this cone of dependency for this particular input will this particular output will change. So, the circuit can be, so in this way if we can do something so that the circuit get partitioned. So, this circuit is divided, so one partition corresponds to this output, another partition corresponds to this output. So, we can now partition the circuit and we can do this testing. So, whether it is possible or not, that depends on the circuit actually, and what we can do some hardware partitioning. So, hardware partitioning, it is possible if the circuit is if this hardware can be modified by the designer, so that this partitioning can be the hardware can be divided into portions, or we can do some sensitized partitioning, where physically the partition is not there, but by applying some control signals. So, this we can sensitize certain paths, as a result other input does not come to the circuit at that point. So, that way we can have some sensitized partitioning. So, whatever we do, ultimately the idea is that we divide the circuits as if the original circuit is divided into a number of sub circuits, and those sub circuits are being tested separately. Okay. So, that is the segmentation testing. Next, after this pattern generator, the next important module that we have in BIST testing is the response analyzer. So, this response analyzer it may do many things, like what is happening is that from the circuit and on the application of every pattern generated by the pattern generator, some response is generated. Now, we cannot store all those responses in the circuit itself, because the pattern generator, so it was running in an autonomous mode. So, it was generating the patterns, they were getting applied to the circuit, but the responses cannot be stored in the circuit, or because that will be huge, okay, for the sake of comparison. So, what is required is that we need some sort of signature. Okay. So, so that after some time we see that okay, this is the signature. So, that signature has to be obtained, and that signature will be compared between the fault free and the faulty cases. So, there are different types of response analysis that can be done, like once count testing. So, we count how many ones we have seen, that may be one type of signature. Like if the circuit is good, maybe we for a set of test pattern we see 100 ones, and in another, if the circuit is faulty, we get 95 ones. So, when we get 95 ones, since it does not match with 100, we say that there is some fault in the circuit. So, that is once count testing. Then there can be transition count testing, how many transitions are occurring. So, once we got a 1 and then 0, or a 0 followed by 1. So, when these transitions are occurring, so what are the transitions, so that can be counted. So, this transition count testing can be done, or we can have some signature analysis. So, signature analysis is the circuit, the whole session will run, at the end we will have the pattern that will be available in the response analyzer. So, that is the golden pattern. Okay. So, that has to be, that is called that will be called signature, and we will try to see whether the signature obtained is same as the golden signature or not. So, to start with, say one count testing. So, we assume that the circuit has got only one output, and the output contains a stream of L bits. Okay. So, the fault free response, fault free output response is R0, R1 up to RL minus 1, and so we are applying some test patterns, say L test patterns, and different since there is only one output. Now, this output is giving us in the first cycle it gave out R0, then it gave out R1, R2, RL minus 1. Then, so if these values are fed to a counter, then the counter will count how many ones were there in that bit stream. Okay. So, that way it is going to be the case. Now, you see that the possibility, the aliasing probability. So, aliasing is that the situation where see maybe that in my in the fault free case, suppose there are 100 ones. So, the my golden value is 100. Now, it may so happen that in the circuit that we are operating, so in one there are two. So, there are due to some fault F1. So, it reduces this fault count by 1. So, it tries to make it 99, but due to the presence of another fault F2. So, this becomes the transition, this one count increases. So, that makes it 100. So, that way at some point for some input pattern where the one should not, for some input pattern where the output should not have been 1. So, that has become 1, as a result one count has increased, and for some other pattern where the output should have been 1, but it has become 0. So, the one count decreases, as a result the one count finally remains at 100. So, we see that this particular situation is not caught, it is a faulty circuit, but the fault is not detected by the system. Okay, so, that is called aliasing. So, faults are getting aliased. So, not only aliasing is not only between the fault free and faulty circuit, it may be it is also between the faults. So, it may so happen that a number of faults they generate the same signature. So, the same signature is equal to the golden signature, then the problem is more severe, because we cannot detect the faulty behavior of the circuit. But even if the signatures are same, but signatures are not same as the golden signature, but still the signatures are same. So, that gives rise to this problem of this a number of faults getting aliased to the same value. And this one, so out of this aliasing probability is given by this expression. So, the aliasing probability that m will be the out of L cases, there will be m ones will be there. So, that will be C L m minus 1 divided by 2 to the power L minus 1. This is the total probability of this aliasing. So, one count testing circuitry is like this. So, we have got this test patterns are applied. So, there is only a single output. So, clock is applied to the circuit as well as the counter. So, after applying all the test patterns, so this counter value will have how many ones it has seen at the output, and that is the signature. Transition count testing. So, this is similar to this aliasing count, similar to this once count testing, except that, so we need to count this 1 to 0 and 0 to 1 transition. So, it is not only the values 1 or ones, but it is also the transition. So, aliasing probability will be given by this expression, and the circuit for this will be something like this. So, this whenever this circuit output is 1, this value is latched here, and you see that there is a XOR gate. So, if previous value was 1 and this value is also 1, then there is no transition. But if there is a difference between the previously stored value and the current response generated by the circuit, so this is they are different, then there a transition will be generated. So, this value will be 1, as a result counter will count it. So, this transition count will get calculated, and this signature will have this transition count value available as the signature. Another possibility is more elaborate. So, that does signature analysis for this type of situation, where for the after applying this entire session, we have got some sort of circuitry where the content of the circuitry will be collected. So, the content of this particular module will get collected, and after the collection, at the end of the session, whatever is there in the collection, whatever is the final collected value, so that is taken as the signature. Now, there are two signature analysis schemes. One is known as serial signature analysis, another is called parallel signature analysis. So, how they are done? In case of serial signature analysis, so we have got an n stage single input signature register. So, what is happening is that this L bit output sequence m. So, this is basically the value coming from the circuit. So, circuit is generating some output. So, that is fed serially into this line m. Now, this output, this L bit sequence can be defined as m0 plus m1 x plus m2 x square plus m l minus 1 x to the power l minus 1, and the polynomial of the modular LFSR be fx. Now, if mx is given by qx into fx plus rx, then the signature of the polynomial is the remainder rx. So, what happens is that when these patterns are actually fed into this structure, so this polynomial, the fx, is going to divide this mx. So, it can be shown that the operation is mimics the behavior of division, and whatever remains in this structure r0 to rn minus 1 is the remainder, and this remainder forms the signature. So, after all the L bits have been shifted through this registers, all through this M, it has come to this LFSR. then we can say that whatever be the content of the LFSR. So, that is actually the reminder, and that we use as the signature. We will continue in the next class on this.